Okay, so again, good afternoon. Ito ay Module 19, so deflection of beams. Okay, so basically this deflection of beams is the same to your strength of materials or statics of rigid bodies, where you find the deflection of beams based on formulas, okay, formulas given from analysis ng elastic analysis. Okay. So the deflection of beams or the limits of deflection for wood beams are required by the IBC or the International Building Codes, and the additional deflection limits recommended by the AITC. Yung actual deflections for a trial beam size are calculated for a known span length, okay, support condition, and applied loads. Deflection may be determined from a traditional deflection analysis, standard beam formulas, or a computer analysis. Okay, the same dun sa binigay natin dun sa steel design. Sa steel design, di ba, may mga different allowable deflections tayo. Okay, then as you can see, the factors that affect the actual deflections are the span length, the type of support or the support conditions, and yung applied loads, di ba? And also kung may framing sila, kung yun yung support conditions, kung framing ba siya, non-framing, kung fixed ba siya or pin, yan. And there are different ways to determine yung deflection, yung actual deflection. Okay? Yung traditional deflection analysis, yung kung saan nagsasolve kayo ng deflection based on double integration method, ano pa ba? Conjugate beam method, three moment equations. Yan. So yan yung traditional deflection analysis. Okay? And also may mga given na standard beam formulas. Okay, if you recall yung mga standard beam formulas, yung mga 5WL raised to 4 over 384 EI, PL cube over 4 EI, yan mga ganyan. And also yung computer analysis. Okay, sa computer analysis kasi gumagamit yan ng stiffness method, okay? And also the finite element method or finite element analysis. Kasi yung deflection analysis, traditional deflection analysis, and yung standard beam formulas, nanggaling yan sa Euler-Bernoulli beam. Bernoulli beam. Okay? Ito yung assumption na kung saan yung plane section daw at every section of the beam, yan, every plane section, yan, mag-cut ka dyan, mag-cut ka dito, are constant or the same. Okay, hindi siya nagde-distort. Okay, walang distortion. However, meron niyang counterpart na Timoshenko beam. Kung saan in this theory, okay, ang theory na to, every plane section meron niyang tinatawag na shear deformation. Kasi kung ganito, let's say ito yung yung cantilever beam end. Okay. Kapag nag-deflect yan, pati yung ends nito, yung plane nito, nag-deflect din. Okay, parang na ganito, na ganyan, yung ends. Meron niyang deformation na ganito. Ang tawag sa deformation na yan is the shear deformation. Okay? The shear deformation. Okay? So, again, sa mga traditional deflection analysis and standard beam formulas, under siya sa Euler-Bernoulli beam theory. Then, sa computer analysis, you can use Euler-Bernoulli beam or a Timoshenko beam. Yan, pwede yan dito. Okay? Sige. So, another trivia lang yan for the class. Sige, for deflection of beams, the actual deflection computation, okay, is comes from the maximum deflection, okay, and it is a function of the loads, span length, and support type, and the beam properties. So basically, we have yung inertia, modulus of elasticity, the length, and the omega. Okay, yung loads. Yan, ito yung length. Ito yung para sa beam properties, inertia and modulus of elasticity. Okay. So yun yung mga mga factors that will affect the maximum deflection of a beam. Okay. So for the deflection criteria, okay, yung maximum delta L mo, which is yung maximum deflection, okay, along the span length, it should be less than or equal to the allowable delta L for initial loading. Okay? Ibig sabihin, ito yung initial deflection. Ito yung allowable initial deflection. So, yung initial deflection galing to sa construction loads. So, syempre, nagko-construct pa lang tayo ng building. Nagko-construct pa lang tayo ng building. And let's say, doon sa second floor, so na-cast na lahat ng beams, nalagay na lahat ng beams. And syempre, lahat ng gamit na dadalhin mo for third floor is nandun sa second floor. So syempre sa mas malapit. Mga formworks, mga rebars, semento, yan, para mas madaling iakyat sa third floor. So yun yung tinatawag na construction load. So chine-check din yung deflection sa construction stage. Then after that, chine-check din yung deflection sa total service loads. Ito yung kompleto na. Ito na yung complete. Okay. So complete loads na to. Okay, sorry. Complete loads. Yan. And the criteria is the maximum total deflection should be less than or equal to the allowable total service loads. Okay? If this criteria does not satisfy, therefore, a new trial beam size will be selected based on inertia, the timbre of modulus of structure of elasticity, and the allowable deflections. Okay? So, ganyan yung pag-determine ng beam size. Diba? After finding the beam na satisfy the strength criteria, the strength criteria are the bending and the shear, kailangan mo pa rin masatisfy yung service criteria, yung serviceability criteria, yung deflection or vibration. Okay? So, there are instances na pasado sila sa strength requirement. Okay? So, either beam or shear, pasado sila, but hindi sila pumapasa sa deflection. Okay? So meron ding instances naman na meron ding instances na hindi sila pumasa sa strength requirement pero pasado sila sa deflection. Okay, meron ding ganung instances. So, dun sa first instance na okay, pasado sila sa requirement pero hindi sila pumapasa sa strength requirement pero hindi sila pumapasa sa beam deflection. So ano yung solution na gagawin ng engineer? So yung solution na gagawin niya, pwede siguro lakihan natin yung beam size. Pwede siguro palitan natin yung compressive strength. Or maybe i-check natin yung loads. Yan. Kunwari nagawa mo na lahat, yung loading, hindi ka pwede magpalit ng properties kasi mapagalitan ka nung limited lang yung budget, limited lang yung client. Okay, at saka mahirap naman na iba pa yung compressive strength nung isang beam lang na yon. Okay? So ganon. So ang natitira sa iyo is yung beam size. Lalakihan mo yung beam size. Pero hindi ka rin basta-basta pwedeng maglaki ng beam size. Kasi papagalitan ka naman ng architect. Okay, yung architectural requirement. So ganito yung nangyayari in most of the time sa actual. Let's say ang requirement lang, minimum requirement ni architect is 2,500 mm clearance. Okay. Ito yung clear height, ceiling to floor, ceiling, finish floor. Pero yung mo lang, yung limit, yung center to center lang nung second floor beam and yung third floor beam, yung every ground floor is 3 meters lang. Yan, 3 meters lang. Tapos nag-design si architect ng 6 meter span. And based on your analysis considering gravity and seismic and wind, yung 6 meter span beam na yon nagre-require ng 500 mm depth na beam. So imagine 500 mm depth. So kinain mo na yung space. So imagine puro beam na to, okay? Ay marami ka pang ilalagay diyan sa allowance na yan kasi may ilalagay ka pang beam, slab, ceiling, ano pa? conduit, mechanical conduit, at saka electrical conduit. Yan. So kinain na agad ng beam mo. Meron ka pang ceiling, meron ka pang mechanical conduit and electrical conduit. And most of the time, yung mechanical and electrical conduit ay 100 mm yung nire-require. Okay? So, hindi ka pwedeng basta-basta mag-change ng deflection. So, meron pa tayong ibang way, ibang method para mapasa yung ating beam. Meron tayong tinatawag na cambering method, the camber. So camber is initial curvature built into a member which is opposite to the deflection under gravity loads. So basically, in other words, ano lang to, meron tayong upward deflection. Nilagyan natin siya ng upward deflection na kapag niloadan mo siya, okay, babalik pa siya dito sa middle, then babalik pa siya dito sa ilalim. So ilan yung i-deflect niyan? So mga 30 millimeters pa yan, let's say. Wag muna natin lagyan. Yan, so meron kang in-upwards mo na siya, then yung deflection pa dito. Okay, so nagkaroon ka ng allowance, ng room. Okay, however, hindi ka rin ganun basta magre-recommend ng cambering kasi meron niyang limit. Meron kang limit na 1.5 delta T. Ibig sabihin, yung maximum cambering mo lang is 1.5 times the dead load deflection for a typical camber sa glue lam beams or glue laminated beams. Okay? So for example, meron kang deficiency na 10 millimeters para pumasa doon sa deflection requirement. Yan yung kulang mo. Yan yung sobra mo pala. Yan yung sobra mo. So gagawin mo, iaangat mo to ng 10 millimeters. Yan, iaangat mo siya ng 10 millimeters. And that is this one. So hindi rin basta-basta yan. Kunwari may 100 millimeters ka na sobra. So ang solution mo ba, ika-cambering mo ba yan? Hindi. Meron siyang limit na 1.5 times the delta D or yung deflection due to dead load. Okay. Yan. And also, pag magka-cambering tayo, meron kayong tinatawag na general notes sa reinforced concrete. Okay, additional ano lang din to. So, meron yung typical general notes na every 4 meters, kailangan mag-camber sa kanilang formworks ng 10 millimeters. So, 10 millimeters every 4 meters. Default yan. Pag nandyan na kayo sa site, makikita nyo na nagka-cambering yan ng 10 millimeters every 4 meters. Okay. So, what are the allowable deflection based on different codes or based on common codes? So we have for flat roofs and floors, we have two deflection requirements, L over 180 or L over 360. And for roof or floors, we have L over 480 or L over 240. Depends on the different conditions. Okay, yung condition na to, either not supporting or attached to a non-structural element, okay, that are likely to be damaged by large deflections. And yung isa, supporting or attached to non-structural elements, likely to be damaged by large deflection and not likely to be damaged by large deflections. Okay? Yun yung mga permissible calculated deflections. And I think napakita ko na rin to doon sa steel design natin. Okay. Okay, what are the common beam formulas tabulated in the AISC? So, hindi lang dito nalilimit yung beam formulas. So meron pang napakaraming beam formulas. But if you can derive all those beam formulas based on method of double integration method, DIM, naalala nyo pa yan? Or conjugate beam, okay, walang problema. Okay, sige. For a simple beam, simply supported beam, in the table 3-23 of the AISC, we have the shear, moments, and deflections. Okay, and the maximum shear, deflection is given by 5 omega L raised to 4 over 384 EI for a simple beam uniformly distributed load. Okay, for a simple beam load increasing, we have this equation, delta max, with which at x equals to ganyan. Okay, simple beam with increasing at the center, we have this formula. Okay. So you can recall all those simple beam formulas. Okay, marami yan sa internet. Okay, then also we have the cantilever beams. So cantilever beams, we have this one. Itong equation na to, ito, and ito. And remind ko lang kayo dito sa tabulation of cantilevers na nalaman ko. Okay, so you can memorize all the deflection formulas sa cantilever beams based on this table. Okay, so please, malaking tulong to kapag magbo-board exam kayo. Yan, ito. And yan. Okay, this all have a length L, omega, omega, P, M. This is M, moments, and moments. Okay, for the deflection, the formula is M L squared over 3 plus N EI. Okay, ano yung M? Yung moment dun sa may fixed support. Okay, so find the moment dun sa fixed support. Eh ano yung N? The N values, kapag ganito yung equation, you have negative 1. This one is 0. This one is 1. This one is negative 1, 0, 1, and 2. Ayan. So, i-substitute mo lang yan dito. Substitute mo yung M. And we'll arrive all those equations. Yan. Equation na yan. Ito and ito. Okay. So, yan yung table of cantilevers. So, parang extension lang to nung strand of materials nyo na nag-find kayo ng deflection. So, ang material lang na ginagamit natin dito is basically wood lang or timbers. So, walang problema. Madaling, kayang-kaya nyo to. Sige, for example, problem 1, a simple 100 millimeters by 200 millimeters beam, which is 6 meter long, is supported at its end. Okay, then it carries a uniform load of 7.5 kilonewton per meter, excluding its own weight of and also the modulus of elasticity is equal to 13.8 GPa. The weight of the wood is 5.6 kilonewton per cubic meter, and the allowable deflection is 33 millimeters, which comes from L over 180. Yan. The problem are compute the reaction, compute the maximum moment of the beam, and the maximum deflection of the beam. Okay. Before we find the reaction of the beam, okay, according to the problem, ang 7.5 kilonewton per meter ay excluded the weight of the beam. Okay, so kasama dapat yung weight of the beam. So therefore, the load W the load omega that our beam carries is, including the beam weight, is equivalent to total W equivalent to the beam weight in kilonewton per meter and the service dead loads. Okay. So finding the beam weight, we have the area times the unit weight. So area times the unit weight, you have 0.112 kilonewton per meter. So you can easily add them since the same sila ng unit. So you have 7.612 kilonewton per meter. So ito yung total weight na kinikerry nito. Okay, so ito pretty basic lang. So WL over 2 for the reaction, you have this equation. This value. Next problem, maximum moment of the beam, you have this value. So WL squared over 8, you have this value. Okay, so next natin is the deflection of the beam. Yan. So before we start finding the deflection of the beam, so let's have a recap lang ano mga units. Okay, recap natin. Ang GPA class, anong unit ng GPA? Ang unit ng GPA is kilonewton per millimeter square. Anong unit ng MPa? That is Newton per millimeter square. Anong unit ng KPa? Yung KPa ay equivalent to kilonewton per square meter, and Pascal is equals to Newton per square meter. And 1 GPa is equivalent to 1,000 MPa. Okay. 1 MPa equivalent to 1,000 kPa. And 1 kPa is equivalent to 1,000 Pascal. And also, meron tayong ganito. Okay. 1 kilonewton per meter equivalent din siya sa 1 newton per millimeter. Please take note of this one. Okay. 1 kilonewton per meter equivalent siya sa 1 newton per millimeter. Kasi nga, kilonewton, i-multiply mo ng 1,000 para maging newton. Yung meter, i-divide mo ng 1,000 para maging millimeter. So, nag-cancel out lang yung times 1,000 and divide 1,000. Okay. So, kailangan natin yan sa pag-solve for the maximum deflections. Okay. So, the formula is 5 omega L raised to 4 over 384 EI. So, hanapin natin yung omega. Omega natin ay, ano ba omega natin? Given natin. Omega is 7.612. The L is 6,000, 6 meters. Okay, 6 meters. The E is 13.8 GPa. Okay. So, hahanapin natin sila. Okay. So, convert natin 13.8 GPa. That is 13.8 times 10 raised to 3 megapascal. The inertia is BH cube over 12 since rectangle yan. So, you have this inertia in terms of millimeter raised to 4. Okay. So, ito, 7.612 is equivalent to kilonewton per meter. Tama? Yung L natin, 6,000. So, naka-millimeters to. So, millimeter raised to 4, naka-mm raised to 4. Okay. Yung E natin is in megapascal. Therefore, yung E natin ay naka-megapascal. So, that is Newton per millimeter square. And yung inertia natin is naka-mm raised to 4. So, basically, pwede natin itong i-cancel out. Okay. Ito, yung Newton and kilonewton. So, again, kilonewton per meter is equivalent din sa Newton per millimeter. So, therefore, pwede natin cancel out si Newton and natitira na lang sa'yo is millimeter square over millimeter. And therefore, yung final answer mo is in millimeters. Okay? So, para hindi kayo malito sa unit, be consistent na lang sa paggamit. Okay. So, para maging consistent kayo, yung L nyo dapat ay naka-millimeters. Yung omega nyo dapat naka-kilonewton per meter or newton per millimeter. Yung modulus of elasticity inyo, naka-MPa dapat. And yung inertia nyo is naka-millimeter raised to 4. Okay? So, going back to the problem, we have 139.621 millimeters. And that is far greater than the allowable, which is 33 millimeters. Therefore, that is not safe. Okay? So, meron kang deficiency na 103.621 millimeters. Okay? And you cannot, 106 pala, 106.621. And you cannot camber, okay, your beam na 106.621, napakalaki niyan, 106.621 millimeters. So therefore, you don't have choice to increase your size or change the modulus of elasticity or change the material. Okay. So, kunyari, na-optimize mo na lahat yung section mo. So, ang sasabihin mo sa architect, okay, assure you that ito, hindi nga siya magde-deflection ng malaki. And maybe you will reconsider itong allowable deflection nyo. Sabihin mo sa architect, as architect, magde-deflect yan ng ganyang kalaki. So kung maglalagay tayo dyan ng glass, sure yan, magka-crack yan. So yan yung mga instances. Okay? So that's it for the deflection of beams. Any question? So sa deflection of beams? Okay. So medyo straightforward lang yung discussion dito. Any more questions before we proceed to next module or next topic? Okay, again, sa pagde-design ng beams, kailangan mong i-consider yung strength and serviceability requirements. So, the strength are bending and shear. And for the serviceability, we have the deflection. Okay, yung vibration, that is more advanced. But sometimes, kino-consider din yung vibrations of beams. Okay, yung